One example of such representation is MFCC, mel frequency substrate coefficients. I prepared another example. Sometimes if waveforms fail, we can use another representation, spectrograms. 3 questions that is good to answer before we start doing any model at all. Hello, I'm Mateusz Szymański. I work as Senior Machine Learning Engineer at DeepSense AI. And after hours, I produce music and explore sound processing techniques. So for that reason, I'd like to talk today a little about the importance of audio representation in the context of machine learning models. I'd like to go through the 2 most common audio representations, waveforms and spectrograms, and explain why the choice of the representation matters at all. At the end of my presentation, I'll try to show you a very compact guide on how to make an informed decision about the audio representation choice. But before I start to explain anything, let's make sure we know what the audio representation is in the first place. So, audio representation is any form in which a sound signal is encoded. So you can think of the representation as a kind of a lens through your model view the audio and which will bring certain details into focus and leave other blurred or even maybe invisible. So I prepared an example that shows different representations of the same recording. So let's hear it. Maybe I'll try to do that once again. So I will talk about these 3 concrete representations a moment. But before, maybe let's answer a most basic question. Why should we care doing ML? Why this choice matters? Nowadays, many audio tasks, especially around speech transcription or text-to-speech, can be handled by large language or multimodal models. However, they are not suited for all audio tasks. Hence, from time to time, you probably may need to create a custom audio model, and the one single decision about audio representation may determine whether your solution is going to work or not. As an example, imagine you build a model to capture which words are being spoken. Not all details in the audio are important to task you try to perform. There are some features of voice that don't change the word, like pitch or intonation. However, we can encode audio in a way that highlights mostly only these features that we care about. And one example of such representation is MFCC, mel frequency substrate coefficients. And this is very compact representation that highlights exactly information about speech, but disregards fine-grained details about pitch itself. So it's used for VOSC, a model that utilizes this exact representation that is shown on the right-hand side. However, if you try to identify who is speaking, rather what they say, discarding pitch information is precisely the wrong thing to do. Pitch, tone, intonation now are essential to the task we are trying to perform. Previously, irrelevant features now become relevant and essential. So as an example, we have another representation, which is log-med spectrogram that makes this aforementioned features apparent. On the second graph, you can see that the general shape of the representation is similar for these 2 words. And the resemblance is a model that uses that representation to capture not the words themselves, but the features like pitch, intonation that can identify the speaker. So the bottom line is, so what counts as noise depends on the task. So to sum it up, why should we care? The way we represent audio impacts the entire system. Usually it cannot be prolonged or delayed, and changing it later is rather costly. And the audio representation determines what information your model can access. So for instance, if you choose a representation that discards information you need, no amount of data or model capacity will recover it. So another point is that the audio representation may set the bar for your resources that you need to train a model or for inference. So these three aspects are important if we are ever going to create a custom audio model. Having said that, we need to understand a little more about sound to get a distinction between properties of different representations. So maybe let's answer a question. What is sound? So sound is a time-varying pressure deviation propagating through the medium. This definition is quite dense, so maybe it's easier to show that explain. So you can see that when pressure changes over time, it compresses some molecules or expands them. And the difference is in the pressure is exactly what we can capture using microphones. So the important part for us that we get an immediate representation from microphones. This is a waveform, exactly this wave you can see. But it turns out that there's a very precise mathematical tool that allows us to analyze the waveform even further. So it turns out that any waveform can be decomposed into sine waves at different frequencies. So we can represent our waveform as superposition of sine waves, the fundamental, that is the one with the lowest frequency, and harmonics, they are integer multiples of the fundamental. So as previously, maybe it's easier to see how it works in practice to get a better understanding of the entire process. So I prepared another example that shows how Fourier transform works in practice. Okay, so Fourier transforms are immensely useful for frequency detection because of that fact. We are going to use that information later on. But now having these basics, we can delve into the most common audio representation, a waveform. So the waveform preserves nearly all information that has been captured by the microphone. For the same reason, it's high dimensional, and 1 second of audio at the standard sampling frequency has more than 40,000 points. So you can imagine it grows quite fast with the length of audio. However, the useful patterns are not immediately attainable for the model. And the frequency patterns are mostly hidden. We cannot look at the graph and see what the frequencies look like in the just looking at the graph itself. So the model needs to learn its own filter to access this information. You can imagine this is something like training a large language model, and before it captures meaning of words, it needs to understand the grammar first. This is more like similar process. And because of that, this increases required data, compute, and model capacity required to train the model. There are certain circumstances when we can afford operating on raw audio data. So first of all, the most important, we have budget for that. Sometimes we can rely on pre-trained models, but sometimes we can have enough data to train from scratch. It's rarely the case though. And the third important point that we care about audio reconstruction generation quality the most. So we need this complete information. But sometimes, for the same reasons that I showed previously, it's generally hard to train such model, especially using naive models. What we can encounter is memory explosion, I talked about the dimensionality of the waveform. We can fail to learn model the global patterns because of the limited scope and of the model. And because of that, the long-range structure of audio is out of sight of the model's receptive field. As an example, so I prepared a convolutional layer network with 10 layers, and you can see that even 10 layers give us pretty low window of less than 50 milliseconds. So it's rather small. It doesn't mean it's not useful, but it's very local, meaning that it's only very small distances from the time period we analyze. Sometimes this may be not a problem at all. So if we decide to go that path, there are some natural model candidates. So good match is, of course, convolutional layers, of course, one-dimensional. Sometimes hybrid approaches involving transformers do the job, so CNNs extract local patterns, but transformers try to extract the longer range dependency in audio sample. And sometimes there are more advanced solutions like encoder quantizer decoder that produce another very interesting intermediate audio representation that allows us to tokenize the music as we tokenize the text. It's called acoustic tokens. This is beyond the scope of this presentation, but it's useful to know about that concept. Of course, there are some poor matches. Raw perceptron has no notion of locality or sequence. Recurrent networks quickly lose the context, so they are not very suited for that task. Okay, so sometimes if waveforms fail, we can use another representation, which is spectrograms. And to make spectrograms, we use something which is called short-time Fourier transform. Essentially, it splits signal into windows, segments, and captures a spectrum I showed within the video previously for each of that segment. And composing this spectra, we get an image-like representation, which is called a spectrogram. So you can see this is a spectrogram of Hello World that was used in the previous example. This is exactly the representation of that audio sample. So what are the properties of spectrograms? Spectrograms are widely used because they have two very nice properties from the perspective of machine learning models. They expose the explicit structure, so we can clearly see frequencies over time. The representation is quite compact. We have a complexity of dealing like maybe wide but images. However, this approach is not perfect. It divides frequencies linearly, but our sound perception is logarithmic. What do I mean by that? So our pitch differences that we perceive are in fact ratios of frequencies, not the differences. So as a result, spectrograms struggle with low frequencies the most. And since all frequencies fall to bands, not precise frequencies, we lose some precision. And it comes with something which is known as Heisenberg-Gabor uncertain principle. So this is one of the most important trade-offs that we need to consider, if we have time or frequency resolution better or worse. If you are familiar with the Heisenberg uncertainty principle, so you cannot get precise measurement of position and momentum at the same time. And this trade-off is exactly the same in our case. If we want to have better frequency resolution, we need more samples, so we need more time. And of course, vice versa. So we cannot get arbitrary precision in both domains. So here are two extreme cases to showcase that. So we've got a spectrogram that is very precise in frequencies, but you can see that it's poor in distinguishing the time. On the other hand, we have very good in time spectrogram, but it fails to recognize frequencies very well. You can even see that the low frequencies in one giant band spanning over 100 hertz, which is a lot, quite. However, you can combine different spectrograms, so you can use different ones. And this is something which is called multi-scale spectrogram. I will talk maybe a little further. And yes, the spectrograms are very good candidates if we rely on frequency information extraction. We need compact models that run real time. And we want to have, we want to expose useful patterns right away. If our task is classification, this is very easy. Spectrograms maybe are not that good in terms of audio generation. Of course, it's not perfect and we need to be aware of certain pitfalls. So if we cannot handle this trade-off I talked about good, then we can train model inefficiently. And if usually operating on raw values from Fourier transforms is a bad idea. Almost always we need some scaling. Log scaling is the classical choice there. And sometimes we need to generate the audio, but we discard phase, and this destroys the reconstruction quality. So the models that are good matches are similar. There are convolution layer networks, transformers for the same result, and hybrid approaches that combine different balances these techniques. As a curiosity, I mentioned refusion, that uses stable diffusion to generate based on spectrograms. However, the output quality is debatable. And worse matches, not that bad, are recurrent networks. They have still limited long-range modeling. And of course, perceptron ignores completely spatial structure of spectrograms. Okay, having that said, we know a little more about this characteristics of this representation. I'd like to end my presentation with a quick guide how to choose the right representation for our context. So before we begin, I'd like to raise 3 questions that is good to answer before we start doing any model at all. First of all, we need to consider, do we need a machine learning model at all? It turns out that many audio-related tasks can be solved by deterministic algorithms. They are very well known and studied. Sometimes we need a good processor for that instead of a custom machine learning model. Secondly, because of what I said about large language models, sometimes we can delegate some tasks to these, especially if they involve speech transcription or text-to-speech capabilities. Often they are in agentic environments, plug to play and easy to use almost out to the box. And finally, sometimes the solution is already there. We need just to take a look on custom implementations and open ways that solve our problem somewhere there. Okay, but if these are not met, we have final 6 questions to answer that can help us to choose right between waveforms and spectrograms. First of all, if we need reconstruction, synthesis, separation, enhancement, it's better to use waveforms for the sake of the quality. Spectrograms are mostly for the classification, analysis, but reconstruction is rather hard for that, for spectrograms. And it comes, of course, with the quality. So if we need maximum quality and we have budget for that, waveforms, especially the intermediate representation like acoustic tokens I mentioned, good to go. Otherwise, we can use spectrograms. And similarly, generative approach that combines all these points previously, especially if we follow the language model like architectures, of course, we can use acoustic tokens once again, tokenize our music or speech or whatever we want to operate on. Otherwise, we can use raw waveforms if we deal with short samples, and spectrograms are fine as well. And if Our task is music specific. There are more niche representations, for instance, CQT or log frequency spectrograms that are very well in logarithmic perception of the sound. And we can utilize that instead of spectrograms. Otherwise, if we don't need that, standard procedures are fine. If we are very constrained in terms of the modeling or in inference of anything like that, there are some compact representations I briefly touched, like MFCC or Bell spectrograms that capture the essentials. Otherwise, we can use other representations. And for the same reason, we want to introduce some inductive bias, especially we have limited data for the model to train on. And in that case, we've got some perceptually motivated representations. Otherwise, we can use regular spectrograms or other waveforms if needed. Okay, so that's all what I have had for you. If you found this useful, feel free to like the video and subscribe for more. If you have any questions, remarks, thoughts, leave a comment below. Thank you for your attention and see you next time.